asteroid was discovered coming into our solar system. From where, we don't know. It just came from outside our solar system, meaning it's from a different star system.
It had a very funny shape. It's shaped like a cigar. It's maybe 5 or 10 times as long as it is across. No asteroid that we know of looks like a cigar. Inevitably, there were people who said, well, are you sure it's a rock?
Oumuamua moved through the solar system without warning. Too fast for any telescope to capture. Too distant for any camera to resolve its shape. And yet, it left behind a trail of clues, too mysterious to ignore.
It moved too fast to be bound to the sun. Very first object that we have found coming to us from interstellar space, from other places.
In the years since its discovery, scientists have tried to reconstruct what it might have looked like. Using light curves, which measure how the object's brightness changed as it spun, they estimated its shape. Using its path through the solar system, they calculated its speed and direction. Through all of this, the James Webb Telescope has exposed something far more powerful than the image. A lens scientists can use to trace its outline. And it is more revealing than anything a camera could ever show. The moment we first saw it. On October 19, 2017, a telescope perched high above Hawaii spotted something strange. It wasn't a planet. It wasn't a comet. It wasn't even something orbiting the sun. It was just passing through. The Pan-STARRS telescope had been scanning the skies as usual when this fast-moving object streaked across its view. For the first few hours, astronomers weren't even sure what they were looking at. It had no tail. It didn't behave like an asteroid. Its path wasn't curved around the sun like most solar system objects. Instead, it was steep, fast, and completely foreign. The object came in from the direction of the constellation Lyra, swept around the sun at high speed, and then shot back out like a rock skipping across a pond. It flew straight through. Its trajectory told scientists everything they needed to know. This wasn't just an unusual rock. It was something far more important. The first object ever observed entering our solar system from another star. They named it Oumuamua, a Hawaiian word meaning scout or messenger sent from the distant past. The name felt fitting. This wasn't just a rock. It was a visitor. It had crossed the blackness between stars to get here. And it might be the only one of its kind we'd ever see. In the first few days after discovery, observatories all over the world began tracking it. But the clock was ticking. Oumuamua was already speeding away. Every hour that passed, it grew fainter and harder to detect. The data we gathered was fast, fragmented, and rushed. But even in that short window, what we saw didn't match anything we knew. Its speed was faster than any natural asteroid ever recorded. Its flight path showed no connection to our own solar system. It didn't behave like a comet, and it didn't match the shape or reflectivity of known rocks. For astronomers watching it slip away, one thing became clear. This was something we'd never seen before. But there was something even stranger than where it came from, and that was the way it moved. The shape that shouldn't exist. When scientists began studying Oumuamua's brightness, how its reflected light changed over time, they realized something strange. The light didn't flash evenly. It rose and fell in a pattern that suggested the object was spinning, but not in a way that made sense. The intensity of its brightness would change dramatically, sometimes every few hours. This told scientists that the object wasn't round or even roughly spherical. It was long, extremely long, possibly up to 10 times longer than it was wide. That kind of shape is almost unheard of in natural space rocks. At first, some believed it looked like a cigar. Others thought it could be flat, like a pancake. But either way, the data showed something strange. This object wasn't tumbling chaotically like most irregular asteroids. It seemed to have a rhythm, rotating steadily on its main axis. In reality, Most studies suggest a mix of both, a complex, non-principal rotation state. Not completely stable, but not fully random either. The more scientists studied its brightness changes, the more questions came up. The surface seemed to reflect light in inconsistent ways. Some parts glinted sharply, like metal catching sunlight. Others absorbed light, giving it a darker, carbon-rich appearance. These reflectivity patterns made Oumuamua appear textured, not smooth, not uniform. It didn't look like a comet, which usually has icy layers that begin to evaporate near the sun. But it also didn't look like an asteroid made of dense rock. It was something else. Even more puzzling was the silence around it. There was no tail, no trail of debris, and no visible gas jets escaping from inside. Most comets leave behind at least a faint stream of particles when they pass the sun. Oumuamua left nothing. And yet, it moved in a way that hinted at energy. Its motion wasn't just spinning in place. It seemed to resist the sun's gravity slightly. As it left the inner solar system, it didn't follow the exact path scientists expected. It gained just a little more speed, too much to ignore, but too little to explain easily. That tiny extra push didn't come from visible outgassing like a comet, and it didn't come from gravity alone. This wasn't just a rock drifting in space. It looked dead, but it acted alive. Something was helping it move. The impossible push. It was already strange. An object from outside our solar system moving faster than anything we'd ever tracked that wasn't a comet or asteroid. But just when scientists thought they had seen it all, Oumuamua did something that defied the most basic laws of space motion. After passing closest to the sun, instead of slowing down, as gravity would normally demand, it sped up. That alone should not be possible. Everything in space moves according to a set of rules. Comets fall toward the sun, then swing back out. If they gain speed, it's usually because they've released gas or dust, pushing themselves forward like a tiny jet engine. It's a well-documented effect called outgassing. But Oumuamua didn't behave like that. Telescopes detected no jets, no vapor, no debris, not even a shimmer of water ice coming off its surface. There was no obvious reason for the acceleration. It was just accelerating, silently, invisibly, without any apparent cause. This was where everything started to unravel. Scientists ran through the possibilities. Maybe it was a comet, and we just missed the tail? But observations from every major telescope, Spitzer, Hubble, and ground-based surveys showed nothing, not even the smallest trace of the usual materials that leave a trail behind. That left a major gap in explanation. So, new ideas started coming in, some more grounded than others. One early theory was that Oumuamua might be venting an exotic kind of gas, something not usually seen in comets from our solar system. Hydrogen ice was one candidate. If Oumuamua were made mostly of hydrogen and it slowly evaporated, it might give off enough of a push to account for the speed increase. But there was a problem. Hydrogen ice is incredibly fragile. It would have evaporated long before it got close to us. In fact, just drifting through interstellar space for millions of years would have destroyed it. Another idea involved nitrogen. Some scientists suggested that the object could be a chunk of nitrogen ice from the surface of a distant exoplanet. Imagine a giant Pluto-like world in another solar system, getting hit by something massive. Pieces of its frozen crust go flying into space. One of those chunks, flat, thin, shiny, travels for millions of years and eventually ends up here. This was plausible on paper. A nitrogen iceberg would reflect sunlight well and might gradually erode in a way that wouldn't leave a visible trail. But the big issue was, nitrogen is rare, even in our own solar system. For this theory to work, there would have to be countless frozen exoplanets out there, shedding huge amounts of material. That didn't sit well with many astronomers, so others tried a different route. In 2023, a study published in Nature proposed something a little more familiar: water ice. But not the ordinary kind we find on Earth. This would be H2O that had been heavily processed by cosmic radiation over millions of years in interstellar space. When this kind of surface gets close to the Sun, it doesn't release dramatic jets or tails. It just slowly changes shape. This thermal desorption could create a small, steady pressure, enough to change Oumuamua's path slightly without leaving obvious signs. This model made a lot of sense to many scientists. It explained the acceleration. It didn't require exotic materials. And it lined up with the fact that no visible outgassing was detected. But even that still left some questions. The most unusual idea came from Avi Loeb, a Harvard astrophysicist who became well known for his bold suggestions. He proposed that Oumuamua's speed increase could be explained by radiation pressure. In simple terms, that's when photons, the tiny particles that make up light, push against an object, just like wind pushing a sail. For this to work, though, Oumuamua would have to be incredibly thin, like a light sail. A piece of advanced technology, possibly from another civilization. Loeb argued that its smooth motion, lack of visible emissions, and unusual shape all pointed to the possibility of artificial origin. Not a rock, not a comet, but a probe, maybe even a piece of debris from a spacecraft. This idea sparked a firestorm in the scientific community. Most researchers didn't agree. They said there wasn't enough evidence. They argued that natural explanations, though strange, were still more likely. But even the critics admitted one thing: they couldn't explain the acceleration. Not fully. Not yet. So the debate continued. Was it radiation pressure? Was it water ice outgassing in an invisible way? Was it something else entirely? While it's impossible to truly know this, what is known is that Oumuamua's behavior broke the rules. And when the rules break, science has to pay attention. This tiny object, no bigger than a skyscraper, somehow changed the way scientists think about motion, heat, light, and material in deep space. And it forced the community to rethink old models of what's possible. And yet, the biggest mystery was still unsolved. Because if we couldn't see what pushed it, could we at least see what it looked like? That question led to one of the most imaginative scientific efforts in recent years. An effort to build an image of Oumuamua without ever having seen it. Reconstructing the image. There was no photo, no snapshot, no close-up from a telescope. Oumuamua came and went before we could ever see its face. But that didn't stop scientists from trying to reconstruct its image. Not a literal image, but a mental one, a scientific portrait, pieced together from clues: how it reflected sunlight, how it tumbled, how fast it moved, what it was made of and what it wasn't. Every orbit, every flicker, every missing signal, all of it became part of the puzzle. At first, the only thing they had was the light. As Oumuamua spun through space, its brightness changed over time. It would grow dim, then suddenly flash bright, then dim again. This kind of light variation is called a light curve. It happens when an object isn't shaped like a sphere. A round object reflects the same amount of light as it spins. A long, thin one reflects more or less, depending on the angle it shows you. Oumuamua's light curve wasn't just changing, it was extreme. The brightness was shifting by a factor of 10. That meant the object wasn't just a little bit lopsided. It was very long, possibly 10 times longer than it was wide. That gave us the first sketch, an elongated shape. But the shape was also rotating in a strange way. Oumuamua was spinning with a stable, predictable rotation. It wasn't a clean spin, but it wasn't fully chaotic either. It was complex, a non-principal axis rotation, which means it wasn't spinning smoothly around one axis. It wobbled, it twisted, It turned, and that kind of tumbling made it hard to guess what its surface looked like. But some clues still came through. As the light changed, scientists could tell that some parts of the object were more reflective than others. A few surfaces reflected light like polished metal. Others stayed dark, closer to carbon-rich rock. This uneven reflectivity gave Oumuamua a strange glinting behavior. It didn't just spin like a rock. It glittered like something with grooves or angles. So new models came out. A picture of something prism-like. That's a long, narrow object, maybe flat-sided, maybe twisted slightly, maybe shaped like a shard of crystal with roofed sides. Smooth but structured, possibly reflecting sunlight in concentrated ways. Some scientists even suggested an iridescent effect, like the shine you get from a soap bubble or oil on water. This wouldn't mean it was rainbow-colored, but that it might have had microstructures or materials that interacted with light in complex ways. That's how the second layer of the image took shape. Not just long and thin, but faceted, possibly grooved, possibly layered. Then came the chemistry. Spectral readings, especially in the infrared, showed that Oumuamua's surface had carbon-based materials. Not life, but organics. The same kind of materials found on asteroids, comets, and even moons like Titan. Similar to a coating of organic molecules. Something like a shell that had formed over millions of years in space. Cosmic rays would have slowly modified the surface, hardening it, making it less volatile. This could explain why it didn't produce a comet tail, even if it had ice deep inside. The crust may have sealed everything in. These organic layers could have changed how Oumuamua interacted with sunlight. Not just reflecting it, absorbing it, storing it, maybe even re-emitting it. This led to ideas about possible thermal control, not from intention, but from structure, like the way certain rocks heat up during the day and stay warm at night. Now the image was growing more advanced. A long, possibly flat or faceted object, covered in a carbon-rich shell, twisting slowly through space, gleaming in some parts, matte in others. But even that wasn't the full picture. Some models went deeper inside the object. What if the outer shell was just a casing? What if the real secrets were hidden beneath? Origin theories. The question of what Oumuamua is led quickly to another. Where did it come from? This wasn't just a rock drifting through space. It moved too fast, too cleanly, and too independently. When astronomers traced its path backward through space, they realized something strange. Its angle of entry didn't line up with the flat, rotating disk of stars, planets, and gas that formed the galactic plane. It came in from a different angle, cutting across the structure like a shortcut, as if it wasn't part of our usual cosmic flow. That alone made it special. But there was more. Oumuamua came alone. Most comets and asteroids we know about are part of a system. They have companions, or at least they've left behind fragments from collisions or dust trails from past travels. Oumuamua didn't. There was no debris with it, no matching objects following behind, no signs that it had broken off from a cluster or belt. It was a solitary traveler, a single object cutting across space, with no origin in sight. This led to one of the first real guesses about its birthplace. It was referenced as a red dwarf star system. These stars are smaller and cooler than our Sun, and their planetary systems tend to be tighter and more chaotic. It's possible that Oumuamua was ejected from one of those systems during the violent early days of its formation. A planet could have collided with another, sending fragments flying in every direction. One of those fragments might have become Oumuamua, blasted out into interstellar space, and drifting for millions or even billions of years until it passed through our solar system. Another theory exists. What if Oumuamua wasn't a full object, but a remnant of something larger? A piece of a shattered planet? Some scientists suggested it might be a sliver of an exoplanet's crust, material ripped away during a massive impact or cosmic collision. This might explain its elongated shape and its unusual chemical makeup. It could be the hardened shell of a former world, stripped down to a strange reflective shard. But none of these answers were final. That's because none of them explained everything. The spin, the surface, the acceleration, the isolation. So another theory started to rise, quietly at first, and only in careful scientific terms. What if Oumuamua wasn't just a rock? Some researchers, including respected names in astrophysics, started asking whether Oumuamua could have been something more, something designed, something sent. The stability of its spin and the shape of its body didn't match what we'd expect from a random object flung across space. It rotated in a way that was difficult to explain unless it had a specific mass distribution or structural support. In simple terms, it spun like something built to spin. Its smooth, reflective surface might be engineered, and that it could be made of a material designed to survive interstellar travel, like exotic metal, hydrogen ice, or something even more advanced. But the big question wasn't just what it was made of, it was how it moved. Because after it passed close to the sun, it sped up in a way that didn't make sense. That's what pushes the next section forward. Even with all the theories of its origin, even with all the possibilities, scientists couldn't explain how it behaved after it left the sun. And that's why they had to ask, could it be artificial? Could it be artificial? The moment Oumuamua sped up, without a comet tail, without gas vents, without any visible push, everything changed. Astronomers expected gravity to pull on it a certain way, but that's not what happened. As it exited the solar system, it moved faster than gravity alone would allow. And it didn't follow the clean curve of a comet either. Instead, its trajectory bent outward, as if something had nudged it. There were no signs of outgassing, no water vapor, no carbon dioxide jets. Nothing that could explain the push. Even when scientists looked for microscopic debris or chemical signatures, they found none. That's not just strange. That's unexplainable, based on what we know about comets and asteroids. So scientists proposed different ideas, natural ones. They said maybe sunlight pushed it, a kind of light sail effect, where photons add a tiny but steady pressure. Others said maybe it was made of solid hydrogen or nitrogen ice, and it sublimated too gently to leave a visible trail. One 2023 study said maybe it vented out trapped water from cosmic radiation over millions of years. These are valid theories, but none of them have been confirmed, and none fully match the data. So scientists did what they rarely do in public. They opened the door to another possibility. Could this be an engineered object? Something built to travel through space for long periods? The idea isn't that it's alive or that it came with intent. It's that it could be a piece of interstellar equipment, a solar sail, a metallic probe, or something like an artificial shard sent from another system long ago. Avi Loeb, a well-known Harvard physicist, made this argument openly. He said the simplest explanation for the acceleration, if we rule out every natural one, could be that it was built. That doesn't mean it was, but it means scientists were no longer willing to rule it out. Even if it was natural, it wasn't normal. It wasn't like anything we've seen before. And that's the key point all three transcripts made clear. Whatever Oumuamua was, it changed our definition of what's possible. It forced scientists to expand the categories, to think beyond asteroid versus comet, to question whether we're seeing space the right way. Because if something like Oumuamua can pass by without warning, without a trail, and without explanation, what else is out there? The legacy it leaves behind. When Oumuamua finally vanished into the darkness, a fading blip headed for nowhere in particular, it didn't just leave scientists with questions. it left them with a mission. This wasn't just about one object anymore. It was about the invisible traffic of the universe, the visitors we miss, the signals we don't notice, the shapes we've never seen. And so, the search changed. Breakthrough Stars Hot, originally pitched as a plan to send postage stamp-sized probes to Alpha Centauri using powerful lasers and ultra-thin light sails, the mission took on new urgency. If something like Oumuamua could fly through space, pushed by radiation alone, then maybe we could build something that small, that fast, and that distant, too. And maybe, just maybe, we weren't the first to try. This inspired a shift in engineering. Scientists began designing new models of solar sails, not as far-future dreams, but as near-future technologies. Lightweight structures that could ride sunlight like wind. Self-stabilizing forms that could handle the chaos of deep space. Materials that could reflect, bend, or even absorb light in ways never tested. Oumuamua had entered the solar system in 2017, but we only saw it after it passed by the sun, after the moment it could have told us the most. So researchers knew they needed better eyes on the cosmos. That's when projects like the Vera C. Rubin Observatory gained support. Set to begin full operations soon, the observatory is built to scan the entire southern sky every few nights, mapping objects, detecting motion, flagging anomalies. It won't just track known asteroids and comets. It'll look for anything that moves the wrong way, at the wrong speed, from the wrong place. Beyond the technology, though, something deeper changed, something harder to measure. That's the science of life, not just how it works here, but how it might work elsewhere. Oumuamua raised the stakes. It forced biologists and physicists to think together. If strange objects pass through solar systems regularly, and some of them carry complex chemistry or engineered parts, then maybe life's fingerprints are more common than we think. And maybe they don't always come in ships. The planetary ejection physics, the study of how material is blasted out of solar systems, became a hotter field overnight. Scientists modeled how gravity, collisions, and stellar evolution might send debris into interstellar space. They asked how many rogue objects like Oumuamua are out there right now, and could some of them be older than Earth itself? Even the questions changed. Before 2017, interstellar objects were hypothetical. Now they were real. Before Oumuamua, we had theories. Now we had data, strange, incomplete, but undeniable. Most of all, astronomy had to zoom out. We were no longer just watching our own backyard, we were peering into the lanes between stars, asking what might be moving across the galaxy not with engines and lights, but silently, without signatures, unnoticed, until the light hits it just right. And when that happens again, because scientists now believe it will, we'll be ready. No telescope ever captured it in detail. No spacecraft ever reached it. But that absence might be the most powerful part of Oumuamua's story, because in place of a picture, it gave us something harder to ignore. A shape built from motion, a texture guessed from how it reflected the sun, a behavior that defied every rule we knew. Oumuamua didn't speak. It didn't slow down. It didn't light up or change course or leave anything behind. But in that silence, it said more than most discoveries ever could. The truth might not come in a photo. It might come in a fragment of motion, a trace of heat, a line in a light curve. The perfect reason to keep chasing it. And that's the image that matters most.